Welcome back to our ongoing exploration of the fascinating world of mathematics. Today, we're diving into a concept that's pretty key to understanding how waves behave. The dispersion relation.
Okay.
You might be thinking, waves, is this about surfing?
Right.
Well, not quite. While ocean waves are a great example, the principles of dispersion apply to a much wider range of phenomena: light, sound, even the behavior of electrons in materials.
Absolutely.
We've got some great material from Wikipedia to guide us through this deep dive.
It's a surprisingly versatile concept.
Okay, so let's unpack this.
Sure.
What exactly is a dispersion relation?
At its core, it's a mathematical equation that links a wave's wavelength, or wave number, to its frequency.
Okay.
What's fascinating about this relationship is that it helps us understand why different waves travel at different speeds in various mediums. Think about light passing through a prism.
Right.
The different colors of light have different wavelengths and therefore experience different levels of refraction, creating that beautiful rainbow effect. That's dispersion in action.
I see.
And the dispersion relation is the mathematical key to understanding it.
I'm curious about how this plays out in a vacuum, a place where there are no physical obstacles.
Okay.
Do waves still exhibit dispersion even in a vacuum?
That's a great question. What's interesting is that even in a vacuum, waves can still exhibit dispersion. For example, electromagnetic waves in a vacuum have a linear dispersion relation, described by the equation ck, where O is the angular frequency, c is the speed of light, and k is the wave number.
I see.
Because the speed of light is constant, this means that the frequency and wave number are directly proportional.
Okay.
This is why the speed of light is such a universal constant.
So in a vacuum, the speed of an electromagnetic wave is always the same, regardless of its frequency.
That's exactly right.
Okay.
But when we delve into the quantum world, things become a bit more complex. Matter waves, which describe the wave-like behavior of particles, have a nonlinear dispersion relation.
Okay.
This means that the frequency isn't directly proportional to the wave number.
I see.
This difference is where things get really interesting because it brings in the principles of quantum mechanics.
Okay, so the relationship between frequency and wave number depends on the type of wave and the medium it's traveling through.
Precisely. Let's look at a couple of contrasting examples to illustrate this point.
Okay.
First, consider deep water waves.
By the way?
Their phase velocity, or the speed at which the crests of the waves move, is twice their group velocity, which is the speed at which the overall wave packet travels.
Interesting.
Imagine a wave moving through a stadium crowd.
Okay.
The wave itself moves much faster than the individual people making it up.
So you're saying that if I drop a pebble into a pond, the individual ripples would spread out faster than the overall disturbance.
Yes, that's a great way to visualize it.
Okay.
And then on a completely different scale, we have something like the electron band structure in solids.
Oh?
In this case, the dispersion relation dictates the allowed energies and momenta for electrons, leading to the concept of band structure. The specific shape of the dispersion relation in a material determines whether electrons can move freely, making it a conductor, or if they are tightly bound, making it an insulator.
That's fascinating. So we've got these dispersion relations affecting everything from ripples in a pond to the conductivity of material.
Yeah.
It's amazing how this one mathematical concept can be applied to such diverse phenomena.
It really highlights the power of mathematics to unlock the secrets of the physical world, wouldn't you say?
Absolutely. And we haven't even touched upon all the different applications of dispersion relations yet.
It's true, we've only just scratched the surface. Dispersion relations have implications far beyond optics. They play a crucial role in fields like acoustics, solid-state physics, and even electron microscopy.
Speaking of electron microscopy, that's an area I find particularly intriguing.
Okay.
Could you tell us more about how dispersion relations are applied in that field?
Certainly. In electron microscopy, we use beams of electrons to probe the structure of materials. When these electrons interact with a crystal, they scatter off the atoms in a very specific pattern. This pattern, known as an electron diffraction pattern, contains information about the arrangement of atoms in the crystal.
I see.
By analyzing the diffraction pattern using the principles of dispersion relations, we can actually reconstruct a three-dimensional image of the crystal structure.
So it's like using the scattered electrons to create a 3D map of the crystal's internal structure.
Precisely. It's an incredibly powerful technique that allows us to visualize the arrangement of atoms in materials at the nanoscale.
Wow.
And it all stems from understanding the relationship between the energy velocity and momentum of the electrons, which is dictated by the dispersion relation.
That's incredible. It seems like dispersion relations have been a real game changer in various scientific disciplines.
Absolutely. And it all goes back to understanding the fundamental relationship between a wave's wavelength, frequency, and the properties of the medium it's traveling through.
Right.
But before we move on, I think it would be interesting to take a quick detour into the history of dispersion relations.
Okay.
The development of this concept has a fascinating backstory.
I'm always up for a bit of historical context. Where did this all begin?
Well, it might surprise you to learn that Isaac Newton, despite his groundbreaking work on refraction,
Right.
didn't fully grasp the concept of a material-dependent dispersion relation.
Oh,
He actually dismissed some research that showed discrepancies with his own measurements of prism dispersion because he didn't consider that the material of the prism itself could influence the dispersion.
that's surprising considering his brilliance.
Even the greatest minds can have their oversights. But thankfully, others picked up the torch. Pierre-Simon Laplace, a brilliant French mathematician and physicist, made significant contributions to our understanding of wave dispersion, particularly in the context of water waves.
Okay.
He developed a mathematical theory that accurately described the behavior of water waves, including the phenomenon of dispersion.
And then, of course, there are the Kramers-Kronig relations, which I've heard mentioned before.
Yes.
What role do they play in this story?
Kramers-Kronig relations, developed in the mid-1920s,
Okay.
are incredibly important because they connect the concept of dispersion to the principle of causality in wave scattering.
I see.
They essentially tell us that the way a wave is dispersed is directly related to how it interacts with the medium and how that interaction unfolds over time.
Interesting.
This is a profound insight because it reveals a deep connection between the properties of a wave, the nature of the medium it travels through, and the fundamental concept of cause and effect.
So they add another layer of complexity and intrigue to our understanding of dispersion.
Exactly. They highlight the interconnectedness of wave properties, causality, and the properties of the medium itself. It's a beautiful example of how different pieces of the physics puzzle fit together.
It's amazing to see how these concepts have evolved over time, leading to a richer and more nuanced understanding of wave behavior. And to think we've only just scratched the surface of this fascinating field, it really makes you wonder what other mysteries and applications are out there just waiting to be discovered. But before we get too carried away, let's bring this back down to Earth for a moment.
Okay.
Why should our listeners care about these mathematical equations that govern wave behavior? What makes dispersion relations relevant to their lives?
That's a great question. It's easy to get lost in the theoretical weeds, but the truth is, dispersion relations have profound implications for our understanding of the universe and the technologies we rely on every day. Waves are everywhere. Light, sound, the very particles that make up matter, they all exhibit wave-like properties.
So understanding dispersion relations is about more than just abstract mathematical concepts.
Right.
It's about understanding the fundamental principles that govern the behavior of energy and matter.
Precisely. And the more we understand these principles, the better equipped we are to harness them for technological advancement and scientific discovery. Think about it this way.
Okay?
Dispersion relations are like a secret decoder ring for the language of the cosmos. They help us unravel the mysteries of how waves interact with matter and with each other, opening up a world of possibilities.
That's a powerful analogy. So what kind of possibilities are we talking about?
Right.
What are some of the potential applications of dispersion relations that we can look forward to in the future?
The potential applications are truly mind-boggling.
Wow.
From developing new materials with tailored properties to manipulating light and sound in unprecedented ways. The future is brimming with potential imagined materials that can conduct electricity with zero resistance, or devices that can bend light around objects, making them invisible.
Yeah?
These might sound like science fiction, but they're all rooted in the principles of wave behavior and dispersion relations.
It's incredible to think about the breakthroughs that might be just around the corner. As we wrap up this deep dive, I'd like to leave our listeners with a final thought to ponder.
Okay.
We've seen how understanding dispersion relations has already led to significant advances in various fields. But as we continue to push the boundaries of scientific knowledge,
Right.
what new and unexpected applications might emerge? Could there be hidden connections waiting to be discovered, connections that could lead to technologies and insights we can only dream of today?
It's an exciting prospect, isn't it? The more we learn about the universe, the more we realize how much more there is to discover. And who knows, maybe one of our listeners will be the one to unlock the next great breakthrough inspired by the fascinating world of dispersion relations.
I wouldn't be surprised. To all our listeners out there, keep those minds curious, keep exploring, and never stop asking questions. Until next time, happy wave hunting.